I was just waiting for that. Okay, thank you, Maureen. We are recording right now, just so everybody is aware. And I want to thank everyone for joining us this afternoon or morning, depending on where you're calling in from. This is our, I believe, 4th webinar hosted by B-CRATOS. The B-CRATOS project is a Horizon 2020 European Commission-funded consortium. We're in our 2nd year. We're looking to create a breakthrough communication platform for brain-machine and intra-body signaling with advanced prosthetics and sensor technologies, all geared towards overcoming a number of challenges facing next-generation BCI systems, neural interface systems, and implantables. One of the areas of our project is focused especially on advancing modern machine learning techniques for decoding movement-related signals and providing sensory feedback in the form of electrical stimulation through this BCI system that we're developing. Paolo Viviani, who's joining us from the Links Foundation, is heading up that effort in Work Package 4. So I'm going to go through real briefly and just do a quick introduction of our 3 speakers today and comment on the format, and then I'll hand it over to them. So as I said, Paolo comes from the Links Foundation. He has a background in theoretical physics and computer science, and now he's a senior researcher at Links. His area of focus is high-performance computing, quantum computing, and systems for machine learning and AI. And as I said, he's focused on those aspects of our project, the B-CRATOS project, and Work Package 4. We also have Dr. Andres Agudelo Toro from the German Primate Center. He's a neuroengineer. He's waving. You can see him over there. He's a neuroengineer working on neural decoding, developing neuroprosthetics for use in virtual applications in virtual environments and robotics and experiments with primates. And he's going to be talking to us about some of his work in decoding algorithms as well. And then finally, Dr. Brian DeCleva is joining us from the University of Pittsburgh. He's a research scientist in the rehab neural engineering labs there. He received his PhD at Northwestern University, studying decision-making and upper limb control in non-human primates. And now he's working with human patients who are research participants at the University of Pittsburgh. And will be talking to us about his work looking at decoding individual finger movements using the data collected from those patients. We'll start with an introduction from Andres, and then he will hand it over to Paolo. We'll talk about some of his work on the B-CRATOS project. We'll go back to Andres, and then finally we'll end with a talk from Brian. At the very end, we'll have time for questions. We ask that you just keep your questions to yourself and maybe type them into the chat window in Zoom, and we'll get to you at the end. Also, please do remember to keep your microphone muted during the talks to avoid distracting the speakers. So without further ado, I'll hand over the webinar to Andres.
All right, so I think you can hear me now. So I think I don't need to tell you how amazing our hands are and all the amazing things we can do and learn to do with them, be useful for our daily life. But unfortunately, sometimes this function fails. And today we will talk about neuroprosthetics and how they could help us and help patients to solve some of these limitations. But in general, the field of neurotechnology has a great potential. And from the many, many diseases of the nervous system, neurotechnologies can offer a potential solution. So in a specific, brain-computer interfaces have had a remarkable progress in the last 20 years. But unfortunately, some of these devices are still quite limited, especially specifically finger movement and dexterous movement. So still very limited. And we have talked about some of the challenges that are still there for these devices. Previously, we had focused on more general challenges, and Paul gave us a great introduction a few webinars back. Hans from DePaset also told us about the neurophysiology challenges, but today we will talk about machine learning challenges, and specifically 3 aspects we have learned in our previous experiments. But before going there, Paolo will give us a brief introduction into the B-CRATOS focus and machine learning and machine learning itself. So I hand off to Paolo.
So thank you very much, Andres. Good afternoon or good morning to everyone, depending on where you're connected from. So I will share my screen now, and I hope that everyone sees it. Is it okay? Great. So Paul already introduced the overall goal of B-CRATOS. So we would like to develop a closed loop BCI that connects a high-speed battery-free implant in the brain to a biomechatronic prothetic hand by means of a 2-way high-speed channel that is running with microwaves through the subcutaneous fat. In this context, we will need to translate the signals coming from the brain into meaningful commands and control for the biomechatronic prosthesis. So we're trying to achieve that by developing what we call a machine learning module that will read the signal coming from the neural implant and will control the prosthesis based on this kind of signal. I won't spend much more time on introducing you B-CRATOS, but I will go on with the focus, which is indeed what we're trying to achieve with this kind of machine learning module. Just to give you some more background, I suggest to everyone who hasn't followed that to look at the previous webinar by Professor Hans Scherberger of DPZ, who is leading the effort of the work package 6 of B-CRATOS for the experimentation of the technologies with non-human primates. And his previous webinar was related to the neurophysiology of grasp decoding, and I think it's really interesting for everyone to have a look at. So what do we mean by neural decoding from neuroprosthetics? The idea is what I already mentioned. So to translate signal that comes directly from within the brain into a control, into commands for a robotic prosthesis. And the main step we typically go through to achieve this goal are implanting an electrode in the brain, typically somewhere close to the motor cortex, but I'm not the expert here, so I don't want to say anything wrong. Then this electrode will pick up the analog signal coming from a large population of neurons that will be pre-processed and turned into what we call a spike train. So a spike train is a multi-channel time series of binary data that can be processed by what we call a decoding algorithm. This decoding algorithm, typically in real time, we would like it to act in real time, processes this kind of spike trains and translates that into commands for the robotic prosthesis. So, as I said, we would like to do it in real time because offline decoding of pre-recorded data is at this time well understood. So there is a lot of literature that demonstrate how we can understand what a non-human primate is trying to do by looking at the neural signal. On the other hand, real-time decoding is really challenging. The state-of-the-art model to do real-time decoding right now are like linear models or Kalman filters, which are very simple. So what happens typically is that either the patient, the human patient, or the NHP that are using this kind of BCIs, they basically learn to drive the model and learn to drive the prosthesis. They're not it's not really the model that understands what is the intention of the patient. Moreover, the neural signal changes over time, maybe due to mechanical movement of the electrode, to inflammatory process, or other effects like or neuronal plasticity, and so on and so forth. So daily retraining of the model is required, either on the model side, but also on the patient side. So there is some time-consuming action that should be repeated every day to retrain the model. What B-CRATOS aims to achieve in this side is to improve the overall accuracy of this kind of neural decoding models, and also to try to reuse as much information as possible between experimental sessions that will enable, let's say, a faster retraining every time. So there will be a lower training effort for the NHP at each experimental session, and in perspective also a lower effort for the patient. What we think is that modern machine learning technique can support this goal, and we're trying to investigate this field. So we don't know, we didn't know the background of the audience, so we wanted to give you a very, very fast introduction to machine learning, which is surrounded by quite some hype in these days. And so I will do this introduction, and I hope that there are no mathematicians or statisticians here in the audience, because it will be very fast and I will say many things that are not really super formally precise, but it should be fine. So we use machine learning to try to find patterns in data for which we don't know an explicit analytical form. Like for physics law, we typically make an hypothesis that has a specific analytical form, like that the position is velocity times time. And then we experimentally demonstrate that analytical form corresponds to the law that regulates the phenomena. In this case, we typically have an unknown function that maps points in a space to points in another space, but we don't know the analytical form of this function. And what we have is just a set of pairs of points in one space and points in the, let's say, in the input space, and points in the output space, what I call here x and y's, which represent the behavior of this function, but we don't know the analytical function itself. So machine learning entails building a set of hypotheses, so basically a set of candidate function, and what we also call learning algorithms that picks the best candidate functions among the hypothesis set. And the final result of this process is a function that approximates the original unknown function. How well it depends on, and also depends on the metric that we define to compare this kind of functions. So to give you an example, a concrete example of what it means, I wanted to start to possibly the simplest example of machine learning that has been known for centuries, and it has never been called machine learning until like the early 2000s, which is linear regression. So in this case, we have pairs of numbers, of x and y numbers in a 2D. Well, each number is a real number, and we have a candidate, a set of candidate functions in the form ax plus b, which are linear functions in the 2D space. And in this case, the learning algorithms is nothing more than a least squares regression that allow us to define the value of A and B based on the set of points we have in this data set. From the simplest example, I would like to show you something a little bit more complicated, which is experiences quite much hype these days, which is convolutional neural networks. In this case, we don't have any more real value data X and Y, but we have input data, which is a set of pixels that forming an image. Basically, we have a matrix. And output data is a digit in this case, because what we're trying to do is digit recognition from a small image that is, let's say, containing handwritten digits. In this case, the hypothesis set is the architecture of what we call a convolutional neural network, that is basically a large set of matrices that are multiplied together to give an output with some nonlinearity inside. And the learning algorithm is called backpropagation with stochastic gradient descent. So basically, we are computing the gradient of what we call the loss, so the distance of the output of the network from the desired output of the network. And we are just adjusting each parameter of the model towards the desired output. And this is, let's say, the other end of the spectrum of machine learning. I would also like to go through some taxonomy, because what I've been showing you in the previous two slides is something that is called supervised learning. So we know the input data, like the X's, and we know the output data, which is the Y's, and we are asked to find correlation between X's and Y's. But there are other tasks that belong to the domain of machine learning, which are, for instance, what we call the unsupervised learning, that is where we have just the inputs and we would like to find some kind of structure in the data. In this case, the typical example is clustering. So we have a set of points and we would like to find clusters, but we don't have anything to compare with. We don't want to find the correlation. That typically comes at a later stage. And we have also what is called the reinforcement learning, which is an iterative approach where also the relationship between the machine learning model and the feedback from the environment is taken into account. The example of this is for instance, the AlphaGo model that has been used by DeepMind to beat the Go world champion a few years ago. Another kind of classification we can do with machine learning tasks is the kind of output data that we have. Typically, we refer to classification, to tasks that involve a discrete output as classification. So that, like the previous one, where we have to classify handwritten digits, and the first example of linear regression, in fact, as regression, where we have a continuous output data. To keep on with the vocabulary of machine learning, we typically as I said before, we typically refer to the training process as the process of showing the model more data to adjust the model parameters to achieve a better prediction of the output. This process, depending on the specific model, like for convolutional neural networks, can be quite expensive, and also depending on the amount of data that you have to show to the model, can be in fact quite computationally expensive, and that will be an important point for B-CRATOS that I will show you later. Another important aspect of machine learning is what is called the generalization. So this is typically the final goal of any supervised learning task. What we would like the model to generalize better. What does it mean? It means that it predicts well unseen data. So we have a data set that we use for the training, And that data set is shown many times to the model to adjust its parameters and to achieve a good capability to predict the training data. But we would like the model to predict also data that has not been shown to the model itself, so unseen data, new data. And this capability is called generalization capability. And here we have a visual example of what can happen with a machine learning model. In this case, in the first and in the last case, the model typically does not well generalize. In the first case, because the model is too simple and cannot really grasp the pattern in the data. And in the last case, the model is too complex and basically learn the data by heart, but does not really understand the structure of the data itself. What we would like to achieve all the times is the middle picture. So a model which is not too complex and not too simple, and can really understand what is the structure of the data without following each data point. Finally, I would like to introduce the concept of feature. So the textbook definition of feature is what is reported here. So an individual measurable property or a characteristic of a phenomenon. Typically, in machine learning, we refer to the inputs as features. So the X, Y's we defined before are features. For the handwritten digit classification, each pixel of the input image is a feature. In classical machine learning, features are typically go through a process which is called feature selection or feature engineering. So we don't typically take the inputs as they are, but we transform them in a space where it's easier to run a machine learning model and to classify or to perform a regression on our data. So to give you an example of what feature selection means, I put together this little example of neural network classification, where we have the simplest neural network possible with two inputs, X and Y, X1, X2, and just one neuron. You can see that the training data is shaped like two concentric circles, and just one neuron is only a linear classifier, cannot really grasp cannot really separate the two data sets. If we keep the features X and Y, X1 and X2 as they are, we see that we need 4 neurons to grasp a little bit the shape of the data set. But what we can also see is that if we transform the input features to X1 squared and X2 squared, and we go back to the 1 neuron configuration, 1 neuron is perfectly enough to separate our dataset. So this kind of process is very common in what we call classical machine learning. On the other hand, this needs typically a very good understanding of the dataset and much human intervention. And that brings me to the hype that is surrounding deep neural networks recently, because this feature selection is very easy, as you can see it in a 2D example where you can visualize your data very well, but it's very complex for high dimensional data and more complex data, like for instance, neural recordings. So all the hype related to deep neural networks is because this kind of networks are typically able to do the feature selection and the feature engineering by themselves. Like the convolutional part of convolutional neural networks is exactly that. So it can scan the image for specific relevant features, and then it will pass those features down to the classification part of the neural network. So that's where the real power of deep neural networks lies. Why now all the hype about deep neural networks? the breakthrough that happened in the last couple of decades has been related to computing power. So deep neural networks has been around for like from the 60s and the 70s, but has been just from the like 2010 or so, when we understood that we could use GPUs, so graphical processing units, for performing the general numerical operations that are involved in the backpropagation and the stochastic gradient descent that are needed to train deep neural networks. And this kind of GPUs are now very common in supercomputers and are very, very efficient to train neural networks, so that we can train models like the large language models that are all the hype today, that can have like more than 100 billion of parameters and are trained with several hundreds of gigabytes of text. So they can really, we can really go very big with the model size. In the context of B-CRATOS, we are not going to reach this scale, but the idea is to give us room to experiment with very sophisticated machine learning models. So that's why training models on a supercomputer is involved in the project. And it's not just that, but models which are possibly very sophisticated and trained on a supercomputer will be then compressed and distilled and deployed on a board that consumes very low power and that will be used to drive the robotic hand. So my introduction to machine learning is over, and I would like to go back to why this is relevant for neural decoding. All the discussion I made before about the feature selection is related to the fact that the typical approach to neural decoding involves selecting channels by hand, selecting the most significant neurons by hand, and this requires a great deal of expertise, of human expertise, to do that. This kind of modern machine learning tools like recurrent neural networks, LSTM networks, and so on, can in fact automate this kind of feature selection. So by adapting themselves, by identifying themselves the most significant features. And we can even think about more sophisticated techniques like reinforcement learning among different experimental sessions, and transfer learning that can preserve information between experimental sessions. So the idea is that, okay, this has led some researchers to treat this kind of deep neural networks as black box magical tools. So sometimes we try to throw data at them and expect good results. This is not always the case. I mean, domain expertise is still very, very, very much necessary. But sometimes putting too much domain expertise in a machine learning model may lead to some bias in the model. So a careful balance between this black box approach and a domain-specific approach is necessary. So in the context of B-CRATOS, we try to start replicating some previous results from literature from the group of Andres Agudelo-Toro, who we'll talk later. And we've been trying to replicate this kind of results with modern machine learning approaches and without too much knowledge about the neurosciences behind. One example that I will briefly give is related to this neural decoding experiment that has been carried on by the DPZ group, in which where a non-human primate was tasked to grasp different objects with different shapes, and the neural activity was recording while the experiment was going on. And with an LSTM neural network, which is one specific type of recurrent neural network, we could actually simulate the real-time decoding of this kind of spike trains recording during the experiment, and basically understand what was the shape of the object that was being grasped in real time with results that are a little bit better than the state of the art. Finally, to get to real-time decoding, as I said, the previous task, while it was designed to replicate a real-time decoding task, was based on a dataset that was fully available offline. So the real challenge here is to move on to real-time decoding, where basically offline validation is not possible, where we don't really classify categories, but we have to infer continuous degrees of freedom, possibly many of them, and the time to train and retrain a model during the experimental sessions is very short. So these are basically the challenges that we're facing, and we hope that modern machine learning tools are able to solve these challenges. I'm done. I will hand over to my colleague, Dr. Andres Agudelo-Toro, and I'll stop sharing my screen.
All right, thanks, Paolo. So next I was going to talk about more specific work at the German Primate Center before and now in the context of B-CRATOS. Let me tell you first about vision. So we aim to develop a full brain-computer interface for full arm control. And we have some objectives. In specific, we would like to leave the animation. Let me. Okay. So we want to use full arm. So this has to be full arm control to individual degrees of freedom of the fingers. We hope to do bidirectional control, so both feedback and action. We are hoping that this brain-computer interface is going to be continuously learning, so it's not going to be static, and the user will, over time, improve its use. And we want to work with data in a form that is private, so that it is not affecting the privacy of the user. So this is our vision. And this approach can combine with machine learning approaches in many aspects. So from understanding of the brain activity to decoding to the compute and feedback, I think machine learning is deep on the possible solutions. So we'll talk about those right now. How are we in this project, in this progress? So as Paolo mentioned, we have already had some experiences with offline decoding and the prediction of multiple objects, and Paolo is also improving on that. We had a second phase of this project already, in which we were able to do in a virtual environment some sort of form of an online decoding using RNNs, and we were able to detect multiple group types. And now we are moving to a second phase of the experiment, in which we would like, with the help of the B-CRATOS consortium, add human-capable devices and also a more advanced technology like LSTMs. And hopefully in the future, we would like to move to humans and to clinical cases. Let me show you a first demonstration of the previous phase that we just completed. So this is basically an example of the monkey performing the virtual task while grasping the a virtual handle in different orientations, only using the neuronal prosthesis. And this is using the Kalman filter previously, but if we add the recurrent neural network on top of that, which I will describe later, the prosthesis can be, the performance and accuracy of the prosthesis increases significantly. So I will divide my talk in 3 parts, or in 3, what we call 3 challenges. One of them is the multidimensional of the data. The second problem is learning and how learning is important. And then the data processing and how to deal with this specific amount of data. So what do we mean with high dimensionality? As Paul already mentioned, we're talking about many neurons. We potentially can record hundreds to thousands of neurons. And we are also at the same time talking about many muscles or possible robot joints. But how do we think about this? How do we develop an idea of how to think about this complex problem? So if you think about spiking neurons, you can also think if you bind them in small pieces of time or in small beams of time, you can treat that as a continuous signal, and that signal evolves over time. If you track that signal in a high dimensional space, you can see that the one specific point will refer to one specific time over this time evolution, combining all signals. And if this is tracked over time, we will talk about a trajectory. This is a way to understand this type of process and to have a rough idea of how to start dealing with them. But that's a trajectory. But over time, this specific neuronal activity could cover many other positions in this high dimensional space. And we will talk in this case about a neuronal manifold, or so some specific region of subspace where neuronal activity lives. Same as in neurons, kinematic activity, either of a real arm or of a robotic arm, can cover some space, some subspace on this high dimensional space. And we will talk about a kinematic manifold in that case. And the process of decoding is going to be a process of mapping high dimensional neural manifold to a kinematic manifold. And Paolo gave us a nice introduction of how some of the basic machine learning concepts, but how do they map in this specific configuration? So univariate regression is a simple, and it's the simplest case. If we have one output variable, and we can just adjust a line to fit and predict the function that is of our interest. If you have more than one input, let's say two-dimensional input on a one-dimensional output, you can also do plane fitting, and this plane will describe approximately what is your function. But how do we think about a multivariate regression, specifically the Kalman filter, which is the basic unit of, or is one of the most basic decoders that we use, and how do we map these high dimensions, and how do we think about? Actually, there is a nice way of visualizing this, and this is if you think of a high dimensional complex manifold, and you have some activity, it's going to be n-dimensional rotation of this specific space on this specific space that is going to fit your desired function. So to think about it, we can think about the transformation from a neuronal manifold, which has some specific shape, through a linear function to another kinematic or subdimensional space. How does the concept of overfitting fits in this approach? And this is something I'm going to need later to show you some of our results. And it is also in principle similar. So if you have a specific function or space in which you have some continuous points, when you map it to another space, when there is overfitting, you will find some holes in your target space. And this is a specific example, number 2, will have been a continuous volume in between, but thanks to overfitting, it's going to end up somewhere else in your target space. All right, so with that done, let's talk about what opportunities are. How can we improve decoders using our approaches? And in the case of multidimensional space, specifically, we will ask, can we improve decoders that are able to produce these high-dimensional features or in a specific the characteristic of the kinematics, which are complex in hand use, and can we use machine learning also to improve performance. And I'll talk about two specific examples in our work. So we are proposing, for example, one specific algorithm that improves the fitting of decoders. And you can think about that again in the context of manifolds. If there is a kinematic manifold, sometimes the subjects will try to execute some activity, which is finally a projection of the neuronal activity on these kinematics. But sometimes it's not going to be what the subject intends, and there is some difference between intention and action. And typical algorithms before perform a trick, which is basically doing a rotation on your kinematics and then refitting the decoder to calibrate it again. And that tends to improve performance. And a typical example has been the refit algorithm, which is proposing, for example, it's a simple rotation of the velocity vectors in the attempt trajectory towards where the subject intended to go, and that improves greatly performance. But we found out in our case that was not helping that much, and we are proposing a new way of doing the recalibration of the filter, and it's just doing a simple projection on the intended trajectory, and that actually reduce error during online experiments and improves task performance in a collision task when there are objects in the environment. And one more specific case to the using machine learning techniques is that when we have a simple decoder, as I showed you in the video, the Kalman filter produces an output. It's actually quite okay, but there is also a lot of noise in the output. And this is what we observe in this specific example. But if we improve the decoder by adding a dense recurrent layer on our pipeline, we realize that using this technique improves greatly accuracy in the output. And this we were quite happy about the result. But then we realized that actually we had to be very careful about how to use it, because if you trained with a few target trajectories, you will realize that for non-trained conditions, the decoder actually sucked and it didn't work so well, showing us a clear case of overfitting. But then we learned that if we performed some intermediate, if we added to the training some intermediate trajectories, that was going to improve the accuracy on this to achieve this specific target intermediate points in non-trained trajectories greatly. Let's see that. So let's talk about the challenge of learning. So I talked about these manifolds, and in specific, for motor control, we have actually a manifold for things like playing soccer. So it's on our brain. Most people, or some people, has the capacity or a manifold for activities like dancing, and that combines well with things like moving your feet. But it's also naturally manifold for using your hands, and that is also in there. But if we're talking about learning to use a prosthetic device, we also have to develop a manifold for that specific activity. And in specific, hand movement is not a simple thing. So hand control has many possible actions, individual movement fingers, shape control, and many other things that we can do with the hands. So this has to be all developed. So in this specific part, I'll talk about what can we learn about this specific manifold. So can we learn anything about the way we move our fingers, for example, or can we use machine learning to help this expansion? And the specific experiments performed by Wei and Cheng in our lab, we had a specific question regarding the movement of individual fingers. And in this task, we trained a monkey to perform combined or individual finger movements with the 3 main fingers of the hand. And she performed these 5 possible combinations, either the single thumb, index, or middle finger, or asking the subject to do both combined movements. And this was a surprise to us when we realized that, although we expected that the combination of the finger movements was going to be actually sort of a linear combination of the activity of the individual finger movements, apparently that's not, seems to be that it's not the case. There are still some aspects to explore about these results, but we are getting information that this is not the case, and this is seen in predictions. For example, trying to predict other movements, so trying to predict number of the finger number 3 from the finger number 1 or 2 seems to be actually pretty similar. But actually, Brian is going to tell us a similar story from his work, which is quite interesting and related to this aspect. So regarding manifold expansion, can we do something about? So we realized that the remap strategy, so the way we were using our decoders and training our decoders, was actually helping expand the manifold. So we saw that we developed a technique in which we progressively teach the subjects to learn different aspects of the head movement. So for example, we started to learn the user's control, so the monkeys control different orientations of the wrist. And then we teach them how to use different hand grip configurations. And then we added specifically different intermediate angles to the training. And we found out that over training, this actually was improving and accelerating learning of the intermediate trajectories. So after the subjects learned to do this specific task, it was easier for them to learn some intermediate angles. And also to our nice surprise, we realized that this learning was also shaping the neuronal manifold, as we can see in the correlations to neuronal activity and kinematics. And finally, the aspect of data. I think Paolo made a nice analogy to this, but I think we have realized many aspects, and I think from our experience, 3 points that we have learned regarding data sharing, that it is not just sharing the data, you have to be responsible about how to share the data and also train other persons and other colleagues about how to use it and what was the experiment and what was the specific questions that you had. Or, as Paolo mentioned, just don't use a model. Just using a giant model is not going to solve. There has to be some knowledge that you have to, and data processing that you have to apply. And as Paolo also mentioned, there are no limits to modern compute. It's not true. This actually, when you go to real-time decoding, this is not longer true. But still, I think there are great examples of how sharing data and opening your data and telling others how to use it has, in the last few years, shown the power of the machine learning community in these aspects. So, can we use this data to model brain activity and how to share data code? And I'll show you some examples of where improving in this aspect. So first example of data sharing was a successful use of our data to the creation of a model for a recurrent neural network model that predicted brain activity from visual features to muscle outputs. So we gave to the model actually only visual inputs, and the model was able to produce the muscles without telling anything about the neural information. And Jonathan Michael, which was the main author in this work, was able to predict with great accuracy neuronal observations that were not given to the model. And there are other projects that are ongoing with data sharing. The specific, Federico Fabiani did his master thesis in the specific aspect, and using the data, he found out that some specific models like LSTMs and ensembles. So combining LSTMs and GRUs and CNNs, you will get much more accuracy in decoding than, for example, CNN networks for classifications. And in specific, there is an ongoing effort to port these decodings into a simpler testbed platform for the FAT-IVC project within B-CRATOS. And as Paolo mentioned, there is an interest in improving the decoding performance, and he has great ideas on how to accelerate training by just using supercomputing as a tool. There is a challenge I want to talk today about. It's something we have worked before, and that is how to stimulate and talk to the brain. It's actually not an easy task. There is the extracellular space is a complicated aspect, and talking to neurons back and stimulating is complex. But we will have a future seminar that where we will describe better these aspects. We promised on the webinar that we will tell you how to help. So there are already some available databases and data sets online and code with data similar to what the one we are using, which are a good opportunity to start playing around. And if you play with this and you found some interesting results, just talk to us and let us know how those things are going. So I talked to you about the capacity for improvement that is still there for BCIs, how this is related to the machine learning aspects. And these aspects map to high dimensions. So we have learned about how to think about those in our project. And we talked about the specific challenges and of course opportunities ahead. And that ends my talk, and thanks for your attention.
Okay, thank you, Andres. We are already a little long, but we definitely want to give Brian an opportunity to present his work. So I hope many of you can stick around for that. I did just want to say that we are recording this session and we'll be uploading it as well. But Brian, take your time. I don't know how long you need, but take whatever time you need. Sorry that we've gone.
I'll try to make
over
it
a little.
Yeah, I'll try to not make it too long. Andres, I think you need to stop sharing your screen so I can share mine. Thank you.
Hey, it's all yours, Brian.
Okay, thanks. There we go. Okay, so I'm going to be talking about kind of what we're currently doing in our lab to approach kind of finger control and using these neuroprostheses for actual real life applications right now. So it's a little bit dialing back. I mean, we've had the talks have led up to these huge visions, which are amazing. And this is a bit step back of like, what can we do right now to improve patients' daily lives and what are the challenges that we're coming up against. So I'm not going to belabor the point. I think everybody understands the great variety of things that we can do with our hands and how useful they are. I'm going to just kind of generally lump these hand control, different types of hand control into two groups. And one I'm going to call postural, and that's basically what we've focused on for the majority of brain-computer interfaces when we're looking at arm and hand control, because they allow us to do very simple things like pick up objects. So this is a still from a video that we have of a participant using a brain-machine interface to pick up a cup and pour marbles into a different cup. So it's very simple, and the quality of control is not great, but it maybe is approaching something that is useful in real life. These other types of movements that I'm going to call dexterous are not really, first of all, we need to understand how to actually decode them, which we've heard about some approaches about how to do that. But also, even if we could decode them, we currently don't even have the hardware to be able to implement it. So we don't have the robotic hands that are capable of doing these dexterous manipulations, even if we wanted to, or even if we had the control signals for them. But what we do have is extended computer access applications. So you can imagine that these participants, we work with participants with spinal cord injury who are tetraplegic. That means they don't have any hand control. So they do, a couple of our participants do have residual upper arm control, but they don't have any control of their hands. And they spend a lot of time on the computer because that's something that they can do, and it brings them, it improves their quality of life. And so they would like, when we ask what they would like to do, they would like to play games. They'd like to make digital art. And our one participant has really gotten very involved in this. Or we could even think about, different types of communication devices for people with even higher level injury who aren't able to speak. We can think about how we can harness the dexterity of hand control to improve the communication approaches that we have for BCI. So we're going to start by kind of transforming this into a laboratory task. And the basic layout is this. We're going to show them 5 buttons on a screen. Each button corresponds to one finger. You can see the green one is the thumb, purple is the index, and so forth. And then we're going to cue them by lighting up one of the fingers and say, when it lights up, attempt to press that finger down, press that button. And we're going to do this for all the fingers, kind of randomly interleaved. And then while we're doing this, we're of course recording from their motor cortex. So we have 2 arrays per participant in the motor cortex, either in the hand and arm area or just the hand area. And we can record from about 200 channels of activity. And now what do we do with this activity? So you can imagine we have the firing rates from all of our, I think this was brought up before, the spiking rates. We've got basically the activity from hundreds of channels. What do we do with it? And one common thing to do, and which is very useful, especially when you have a limited amount of data, which I'll touch on again later, is to reduce the dimensionality of the data. So we're taking hundreds of channels and reducing them down to about a 10 to 20 dimensional space. And here we're using factor analysis, which is kind of a standard dimensionality reduction technique. And so now instead of hundreds of channels, we get 20 maybe different dimensions of activity that we can start to interpret and try to use for understanding how the hand is being controlled, or how the participants attempting to control their hand, and then use that for decoding. So here's for the thumb, and then we can overlay all the fingers, and you can see that you can start to make some, you can see differences between the different fingers, which is good if we want to decode which finger the participant is actually trying to press. And now we need to do something with this, turn it into control. And I'm going to go back to just the basic broad view of generally how you would do this, right? So we have our predictor variables, which is all of these factor projections. So it's this low dimensional representation of the neural data. And we'd like to feed it through a decoder of some kind and get the output. And the question I think that I find interesting is, what should the output be? I mean, this is what we want. We have different button presses, so we know kind of what we want the output to be. But is that the best approach? Maybe we should be decoding some other related feature that we can then turn into this output, but not this directly. And so we'd like to understand what kind of activity there is in this cortical activity, what kind of responses there are in this cortical activity that we can use for control. So the first thing that we can do, and I'm going to kind of gloss over all of the specific manipulations that we do of the data to try to these different views of how we orient the axes and all of that. I'm just going to kind of give the broad overview of what we've found. So we found that generally you can find these very non-specific responses that are very prominent and very useful for control because they are very big. And these are related to, like you see here, these are projections onto these specific, or I should say non-specific axes for the different fingers. And they look like There's a transient response at the onset of when they're attempting to press any finger. There's maybe a sustained response throughout the press, and then there's a special non-specific transient response at the end when they release. And now we'd like to say, well, we know that there's information about the specific finger, so we have these non-specific responses. Now let's look for finger-specific activity, finger-specific responses. And so if we line this up here, this finger specificity plot is really just looking at how well can we separate the different fingers from each other at each point in time throughout the trial. So again, this is from basically the time of a press to a release. How well can we separate index finger from middle finger and so forth? And you see that there's this profile where right after the onset of that non-specific response, we get very good separation of the different fingers, but then it decreases and it kind of degrades over time. And so if we look just at the peak there, which is right after this onset that we can detect, we see really nice separation of the different fingers. So this is a plot of the using LDA, so linear discriminant analysis, to separate the different fingers from each other. And so now that we've learned something about what is going on, the different types of features that are actually present in the neural activity, we can go back to our decoder framework and kind of update our approach. And so now, instead of taking our factors as inputs and trying to directly output the full finger press that we want, we're actually going to split it into different kind of subtasks that we think the neural activity is better positioned to do. So detecting onset and detecting offset seems much more reliable than detecting the press just on its own. And likewise, we can limit our scope of when we need to identify the specific finger, because this information about which finger they're attempting to press is not consistent throughout the whole trial. There's a peak, so we can kind of limit our scope and help boost the performance of the classifier that we're using to kind of improve how well we can identify the finger. So now, using this new approach, I'm just going to walk through basically how it works. So we're going to, as this decoder is running online, it's looking for this onset feature. It's trying to pick out when we see this non-specific onset type of event. When it finds it, then we start to classify, because we know that right after we detect this onset, that's where we're going to see the peak of finger-related information. So we're going to start classifying which finger we think it is. And we're going to build up confidence over a few samples about which finger. When we get sufficiently confident in which finger we think the person is trying to press, then it clicks that button, or produces the relevant output. And then it's going to keep it on until we detect that offset event, right? So that non-specific transient that was at the end of each press. And so, unlike the pile of data that the comic that was shown before, where we're just throwing things in and hoping we get what we want out, this is a much more tailored approach, right? We're looking for specific features and kind of building up to the decoder that we want. And I think the benefit for us doing it this way is that the more complicated the decoder is, or the machine learning AI approach is, the more data you need. And that is especially problematic for our situation, where we're working with actual human participants who want to use this and don't want to do an hour worth of calibration in order to train a model that works, as well as they want it to. And so, taking this approach, we're taking a bit of a shortcut, So if we had enough data, if we could collect an hour of participants pressing different fingers, we could probably build a recurrent neural network model that would produce an output that is similar, but we kind of found those nonlinearities that are important ourselves, right? We've identified that there are certain nonlinearities in the data that we kind of know exist. And so we're going to exploit that by looking for those features directly and then building it up ourselves. And that way we can kind of bypass some of the extra training data that we otherwise might need. So there, obviously there are approaches, and hopefully down the line we can start to incorporate data from different days and build up large data sets and not worry about drift over time and all these things that become very problematic when you want to add different calibration sets together. But for right now, it seems like perhaps this more targeted approach helps us boost our performance over what we would otherwise be able to get. So here I'm going to show a little video of the participant using this decoder online. So on the left, the task is basically, again, one of the buttons will light up white. The participant will then try to press that button. And whatever button the decoder identifies as the intent will light up in the solid color. And on the right, I'm showing different projections of the neural activity. So you can see how the different components of the decoder are working together to produce the output. So it's going to start showing this projection that highlights the differences between fingers. And then it's going to rotate to show a different view that highlights the onset offset type of component that we're using to trigger the click and unclick components. Just let this play and see that the performance is actually quite fast. He's able to identify and click the appropriate button within half a second or so. So here we're now going to rotate around to look at a new view of the data that is highlighting kind of the onset offset component that's also part of the decoding approach. So looking across, this is about 500 different button presses. He does very well at this, nearly perfect. And over a few sessions, he achieves somewhere around 50 clicks per second, per minute, which I think is pretty good and is starting to approach, what would be necessary for real applications that you'd like to do with all these different finger presses, like gaming or using different shortcuts for either typing or creating art or doing whatever you want to do on the computer. We did this with our second participant as well. The performance wasn't quite as good. This participant has had these arrays implanted for about 7 years, and they're split between arm area and hand area, so we don't get quite the hand-related activity that we do with the other participant. But still, it does a decent job. And this is kind of the hardest case that we can come up with each different finger. If we just limit it to a couple fingers, say if he wants a few different types of buttons, or maybe you want to do left click, right click, we can do that with almost 100% classification accuracy. But with this hard mode with all the different fingers, it gets a little difficult. And maybe improving the methods that we're using for the classification and so forth would help improve this as well. So now I'm just going to go, that's kind of the engineering part of what we've achieved in terms of control, but now we'd like to also take a look at trying to understand what's happening in the brain or what different components there actually are when the participant is doing this kind of button pressing task. So I showed before this one two-dimensional projection that highlights the separation between the different fingers. But actually, if we do a different type of kind of decomposition of this data, we can find that there are individual dimensions in the neural data that correspond to each finger. So you've got one axis of the activity that looks like it contains only thumb-related activity, and same for index, middle, so forth. So we kind of have one dimension of activity per finger. And so now we can start to ask, and Andres brought up the combination of fingers. What happens if you try to do multiple fingers at one time? So here I'm highlighting again these finger-specific dimensions of the activity. And now asking, what happens when we ask him to push 2 at the same time? So thumb and pinky. And a bit surprisingly, we found that nothing really happens on the finger dimensions that we identified. The projections are quite weak, and we can't really identify from it that he's trying to do thumb and pinky, even though we know what thumb and pinky look like separately. Together, it looks different. And we can actually find a new dimension in the neural activity that is specific to that combination, pinky and thumb. And we can do this with different combinations as well. So thumb and middle, again, has very weak projection on the individual finger axes, but there's a completely new dimension that contains this combination. Same for same for index and ring, and same for a 3-finger combination as well. So it's not exhaustive, and we kind of need to do more about characterizing how these combinations, the fingers do or do not combine for a whole bunch of different combinations. But at least for these few that we've tested, it doesn't look like it's going to be possible to generalize from individual fingers to their combinations, at least not very easily. Right. So each finger and combination occupies a unique neural dimension, which is problematic if you're trying to build a decoder that's going to generalize, right? So ideally, we'd like to train on just, press each finger a couple times. Here's your decoder. It can do anything. And it doesn't look like that's going to be possible, at least not with our current methods. Another way to look at this is just a kind of a different way of trying to understand what's happening. We can try to take our data. So this is a data set in which he's pressing either individual fingers or combinations of fingers. And we're going to split those into just trying to classify the trials with individual fingers from each other, and just trying to classify the trials with combinations and trying to separate those from each other. So if we start with our full space, you can see that we can do a pretty good job of separating each of those. Right. So this is offline data, I should add. This is not online. Now what we're going to do is take out a dimension that is really useful for separating the fingers from each other, the individual fingers from each other. We're going to take out that dimension, and we're going to try it again in the remaining lower dimensional space. So we started out with 20 dimensions. We're going to take one out that is useful for separating fingers, separate individual fingers from each other. And we're going to try again to classify the fingers and to classify the combinations. So here is the result after taking out 1 dimension, 2 dimensions, so forth. And as we progress, you see that the target confusion matrix is degrading quite rapidly and this makes sense, right? Because we're taking out dimensions that are useful for classifying the fingers from each other. So it should be getting worse. But the classification of the combinations doesn't change very much. So here we're already down to, I would say, we're close to chance here for fingers. And we've seen very little decline in our ability to classify the combinations. So this is highlighting that there really when we add new combinations of fingers, we're actually kind of expanding the dimensionality of the neural activity, where there are new dimensions that are containing this activity that weren't there before. And again, that's kind of problematic for building a generalizable decoding approach. So I'll wrap up. I won't take you too much past the scheduled end. So I'm going to wrap up by saying that we can achieve high quality finger decoding by kind of custom building a decoding approach that uses both non-specific and finger-specific components of the neural activity. But single finger activity does not generalize, it doesn't seem, to multi-digit control. We can't just take what we know about thumb and pinky activity together and combine them to know what the output would be for the combination of thumb and pinky. And so the question becomes, how can we calibrate decoders for generalizable dexterous control? How can we have a calibration set that the participant can run through in 5 minutes, 10 minutes, and achieve high-level control across a whole bunch of different applications? And I don't have the answer, so I'm hoping that somebody here can take that and run with it and give me the answer of how we can solve this problem. But I'd like to thank you for sticking around and for your attention, and thank all our collaborators at the University of Pittsburgh and the University of Chicago. And if anybody has questions, I'd love to hear them, or you can contact me, the email below. Thank you.
Thank you, Brian. It's a really great talk. And I'm sure there's got to be, I have a lot of questions, but I know how to find you. Is there anybody else who maybe has one or two quick questions for any of our speakers? I know we've gone over already, but if anybody has a question, please feel free to jump in. We will be posting the video, and if you want to contact any of the speakers from today, we can also provide that information. Yeah, I'll ask real quick, Brian. When you were talking about generalizing, training these models with your participants, are you retraining the model every morning, or can you every day, or can you take a model from one day and apply it to the next? Are you guys doing anything special for that?
So for right now, we've been retraining each day when we do this. We definitely have, it's been a very popular topic, I think, in the field of combining data across days and creating decoders that can generalize. And they generally take the form of, we've got a low dimensional representation of the neural activity. You can, take this low dimensional activity from day one and this low dimensional space, and then rotate them to match up. And now your decoder that worked on day one works on day two. So presumably we can do the same thing. We haven't done it mostly just for implementation reasons. So we're starting kind of at the simplest of just calibrate and use it. But yeah, certainly combining across days is going to be beneficial for an actual end product. If you're, the more data you have, the better it should work, ideally. And you showed with P3 that your decoding was much better. And yeah. I'm assuming the implant is much fresher, so to speak. Newer implant, and also in a very hand-focused area. So we actually, with this participant, right off the bat, could do these finger-based tasks really well, and struggled with center out, which is kind of the standard control. And he had a lot of trouble with it because that relies on a lot of, at least how we would normally instruct the participants to think about it. It involves a lot of upper arm imagery, and the arrays just were not in the right spot to pick that up. So he's since kind of found a type of imagery that works really well to achieve translation. But yeah, I think it's largely it's a combination of both the newness of the implant, which means we get a lot more signal, and also just the location. And are you using spikes, or is this more like just the raw data with some filtering? We're using spikes, yeah. So it's spike data that is then filtered, just simple smoothing. Okay. Yeah, we'd like to expand to a lot of, we've seen good results from other groups who've used things like spike band power or including some of those other types of input data might be useful as well. Right. Yeah, I was thinking about if somebody has an implant that's quite a bit older, that you might get that instead. So, okay. Does anybody else have any questions or thoughts? If not, I'd like to just thank all of our speakers for joining us. Sorry we went over today. I think this is probably the second time in a row we've gone over, so we may just have to start scheduling these either slightly longer or just coming up with a better system to stay on track. But thank you, Brian, for being patient with us, getting to you at the end. Thank you to Paolo and Andres for organizing this and inviting Brian to present at our webinar. And unless anybody has anything else to say, I'll declare the webinar over. And thank you all very much for your very interesting talks.